typical unbalanced system contains an eccentric body, A, rotating at a certain distance about a center axis attached to a second body, B, constrained to move back and forth. If the body, A, rotates with angular velocity, omega, it has angular momentum equal to its moment of inertia, relative to the rotation center, multiplied by the angular velocity. If the motion of the body, A, is given in terms of the tangential velocity, at a given point of the path, its angular momentum is equal to its mass multiplied by the tangential velocity and the radius of rotation. In the process, the body, B, gains linear momentum, that, at the same instant, is equal to its mass multiplied by its velocity. The problems with the old popular description of this process are the following. First, the centrifugal force, considered the cause of the acceleration of the body B, does not exist. Second, there is no way to identify the reaction to the acceleration of the body B. Therefore, the process contradicts the third law of motion. Third, there is no way to explain the increase of the momentum of the body B. Therefore, the process violates the principle of conservation of momentum. For greater clarity, the new approach will be applied to the system free of constraints. The body, A, is accelerated and then starts a rectilinear uniform motion, with a given initial linear momentum. The moving body A engages the tip of a thin rod, whose opposite end is rotatively attached to the body B. Since the body A is moving in rectilinear motion, and the body B is at rest, relative to a non-accelerated observer, they start the inertial confrontation. Their inertial tendencies are contradicted, the body B is accelerated, and the path followed by the body A is not circular. The body A resists the incurvation of its path, which is acceleration. This resistance causes the acceleration of the body B. The body B resists the acceleration. This resistance causes the incurvation of the path followed by the body A, which is acceleration. The reciprocal accelerations of the two bodies occurs in accordance with Newton's third law of motion. To verify the conformity of the process with the principle of conservation of momentum, consider the interaction of the bodies in a given point of the path followed by the body A. At that point, moving in its non-circular path, the body A has a tangential velocity, v. The inertial resistance of the body B to the acceleration acts upon the body A as a centripetal force, which is not orthogonal to the tangent to that point considered. The centripetal force decomposes into two components. The component normal to the tangent, which defines the shape of the curved path. The tangential component, coincident with the tangent to the path, opposite to the direction of the motion, causes the deceleration of the body A. At the same time, the inertial resistance of the body A to acceleration, that is, incurvation of its path, acts upon the body B as a centripetal resistance. That causes the acceleration of the body B. Therefore, momentum is transferred from the body A to the body B, which means that the total momentum remains conserved. In the same way, in the process of inertial confrontation, kinetic energy is transferred from the body A to the body B. This new approach, starting from the fact that the centrifugal force does not exist, finally explains how the process is in accordance with Newton's third law of motion and the principles of conservation of momentum and energy.